Hello YouTube, my name is Tim Sander and I'm going to try to explain a problem that involves some physics, some trigonometry, and some algebra so that we can figure out, basically I want to build a winch and ramp system to load crates in and out of my truck. What size winch do I need to buy to be able to pull the 400 kilogram wooden crate up a Teflon coated ramp? The coefficient of friction between wood and Teflon is 0.15. And then you can tell we have the angle of the ramp there. The cable is pulling at a different angle up to the pulley there, so we need to figure out all the variables. Okay, so we want to solve for the tension force. To do that, we need to know the angle that tension is in relation to all the other forces going on. We're going to call that angle phi. To solve for that, we need to solve three triangles in this equation. We have this triangle formed by the ramp, this one, and then finally this one, which involves our phi. So the first one, we need that angle also. That angle is theta. We know that because we know the length of the ramp and the height of the tailgate there. So we can solve to get our theta. Our second triangle is formed here between between that first one and the second one. And we need to solve for the length of the hypotenuse there, which we can do by taking the square root of 6 squared plus 2 squared. That gives us a length of 6.32 feet. We add that to the 10 feet remaining of the truck, and we know the height of that last triangle is 4 feet. So finally, we can solve for a phi of 13.77 degrees. Okay, on to the physics. So Isaac Newton's first law of motion tells us that if an object is in rest, as this crate is, it's going to stay that way as long as all of the forces that are acting on it balance out, as long as they all equal zero vector. So we want to find out how much force does it take to move it. So we want to break that at equilibrium. The only way this crate's going to go up the ramp is if the force of tension is large enough to overcome the force of static friction, which is opposing it. So now we get into showing all the forces acting on this crate. So we've established that the sum of forces acting on our crate right now equals zero vector because it's sitting still. And we want to solve for the force of tension required to pull that crate out of equilibrium, get it to slide up that ramp. So we're going to draw a force diagram to give us a visual representation of our forces. It's going to help us piece together the math. Now, we could draw it as it's sitting here. We have our x-axis, our y-axis. We have gravity as the only one that's pulling directly along one of those axes. So when we go to add in our other forces here, we're going to have some trig functions, some math. So if we just rotate our x and y axes, because really all that matters is the magnitude and the relation of these forces to each other, we come up with a simplified force diagram here. We have our normal force, friction, those are both pulling on the axes. Gravity's at a little bit of an angle, and our force of tension here is actually dipped a little bit below because the angle there now is our phi minus theta, and that's the relation of tension force with respect to the ramp. All right, so we have our force diagram that shows all the vectors. Time to bring it home by adding all those vectors together. We do that by adding them in their x and y scalar components. So in the x direction, we have t cosine theta minus mg sine theta minus the force of friction. That gives us 0. The y components, we have the normal force minus t sine beta minus mg cosine theta, and that gives us 0. Since we're trying to solve for t, we want to find something to tie these two formulas together. The force of static friction does that because it's modeled as the coefficient of static friction multiplied by the normal force. So what we want to do is solve for the normal force in the y formula, plug it in where it goes in the x formula. So I'm not going to do that here because I don't have time, but feel free to pause it. You can see all my algebraic steps here. We plug in our numbers finally and come up with a force of 676 newtons required to break this out of equilibrium and pull it, which is equal to about 152 pounds of force. So you don't need a very big winch to pull something that's close to 900 pounds. Thank you for watching.